Today we're going to be going over soil and soil erosion. And oftentimes we don't really think of soil as being an earth resource, but it really is a resource for us because without good soils, we are going to have major issues with agriculture. We're going to have big problems growing things if we don't have good soils. So soil becomes a vital geologic resource for us. Now, when we look at materials covering Earth's surface, you might have what's called regolith. And regolith is any unconsolidated surface material. So any broken up bits and pieces of weathered rock sitting on the surface counts as regolith. Soil is a little bit different. Soil is this unconsolidated material, broken up minerals, organic matter, and water. It forms in place on the surface, and here's the really vital part of soil: it's able to support plant life. So the difference between soil and regolith is just kind of broken up rocks. Soil has organic matter and water in it and is able to support plant life. That's the really big difference. And there are many different types of soils that exist, and they have different colors. Some have a lot of white. Some are kind of a darker color like this. This is actually a soil that was buried by a volcanic eruption. This is volcanic material above that. Some soils are living. This is called cryptogamic soil. There's actually cyanobacteria in there, and they kind of secrete this ooze that holds soil particles together. And these like to grow in arid places, so that's kind of like living soil right there. So what I'm trying to get at is there are all kinds of different types of soils in the world. And what we're seeing on this map, each color corresponds to a different major category of soil. So you can see all kinds of different colors for all those different soils we have. If we zoom on into the US, we see again all sorts of different soils in different locations. Even in Texas, the soils that exist are rather varied. And we'll be learning what some of these different names mean when it comes to soils. And an interesting bit of trivia for you is, just like states have an official state bird and fish and the official song and all that kind of stuff, every state has the state soil. And for Texas, the state soil is the Houston Black. And this is basically showing you what the Houston Black looks like. It gives you a description of it, and it shows you where it is located in the state. So if you're ever curious about different state soils, I mean, right now, being stuck at home, we all have a lot of time on our hands. Go ahead and Google list of state soils, and you can maybe win a Trivial Pursuit if you have weird questions in that. So anyway, this is something we don't want to see with soil. We don't want to see this kind of erosion because, like I said earlier, soil is a resource that helps us with agriculture. And so when we have things like these big dust storms, and so that's just you know, not a good thing for us to happen. It's also bad for your health in inhaling soil and sandy material like that. And when you have dust storms like that, it also reduces how much plants can grow in places. So in lecture today, we're going to take a look at how soils form, what different types of soils we have, and how we can prevent soil erosion from happening. So soils are created because on Earth's surface, rocks will get weathered, right? One part of the soil is this weathered rock material. So how do we weather rocks? Well, there's two major ways we weather rocks. We can weather them mechanically, which is the physical breakdown of rocks with no change in composition. Basically, you have one big rock, you break it apart, you have two smaller rocks, same composition. That's one way, is this mechanical weathering. The other way is chemical weathering, where the actual chemical composition of the rock changes. But let's look at a few mechanical weathering processes. You can have something called frost wedging. Frost wedging occurs because water is a very special substance. Unlike most substances that get smaller when they go from liquid to solid, water actually expands. It gets about 9% bigger when it goes from liquid to solid, and that has to do with the way the water molecules are. But anyway, if you have a little crack in rock and it freezes and this ice then expands, it's going to exert a force that will start splitting that crack wider and wider, and ultimately could break the rock. Similarly, you can have salt wedging. In this case, instead of a crystal of water, right, instead of ice crystals growing in a crack and pushing the rock apart, you get salt crystals growing in a crack, pushing the rock apart. And we can see that here. This is often Petra. Notice it looks like it should be flat up here. We got these weird little holes in there, and that's where salt crystals can form and slowly break apart this sandstone. Root wedging is another way rocks can get broken apart, and in this case the roots of a tree grow into the rock, and as the roots get bigger and bigger and bigger, they can force the rock apart. So we can see we have this tree here and this root growing into those rocks. As that root grows, it can break some of those. And that's what's happened right here in this particular rock. This used to be together. That is the root of a pine tree. And as that pine tree grew, it ultimately split that rock into two. And then we have pressure release. Pressure release is a type of mechanical weathering that only occurs in rocks that formed deep, deep underground, like igneous intrusions, igneous rocks like granites. So this rock formed deep underground, many, many miles down below the surface, and so there is all sorts of pressure pushing on that rock. Then when this rock above it erodes away and this rock is exposed at the surface, it starts expanding a little because it's not being forced to stay together anymore. I always say this is sort of like when you take the outer skin off an onion and it kind of splits apart a little bit. That's what happens to this. When there's not all that rock kind of holding it together, it's going to start splitting apart. You're going to get these cracks developing. We call those sheet joints. And slowly that igneous rock is going to break into different pieces. That's what we're seeing right here. This is a Pikes Peak granite. This piece and this piece used to be completely stuck together, but we have this crack that has developed in it. Now those are some of the basic types of mechanical weathering. I said we can also have chemical weathering, where the actual chemical composition of the rock is changed. And this could be in the form of dissolution, where minerals are completely dissolved in water and washed away. You see that in things like limestone, in this headstone, which is made from limestone. It's hard to read because much of the rock has already been dissolved away by rain hitting that. Or you can have things like oxidation and hydrolysis. These are other chemical reactions between water and the minerals and oxygen that can alter the composition of that rock. And right here you'll see these kind of reddish zones in those lava flows. And that's where oxidation has happened. Some of the iron minerals in those lava flows basically have rusted. See the sheep? Okay, so ultimately we have solid rock, bedrock, being weathered both mechanically and chemically, and through additional processes can end up creating all those different types of soils that we have on Earth. And there are 5 main things that control the type of soil that you get. One is the parent material. Basically, what what rock is being weathered. Is it basalt, or is it sandstone? Is it limestone? And that's going to affect the type of soil you get. Also, soils tend to be better developed on flatter ground. So the slope is important to soil development. It does take quite a bit of time for soil to form. So the longer a surface is stable, the thicker and better developed your soils will usually be. Biologic activity is important. Remember, one of the parts of soil was organic material. And where does that organic material come from? Biologic activity. And then climate. Climate is like the most important thing affecting the type of soil you get, because our climates in deserts and in rainforests are so different. The temperature, the amount of precipitation varies so greatly. That's one of the big things. In fact, that's the biggest thing that's going to affect the type of soil that you get in different places. So just to show you how climate can really affect weathering, I'm going to show you this headstone again. This was made out of limestone, and this was put in place in 1882. And it's very, like I said, rather hard to read because it has been exposed to quite a bit of chemical weathering. In this case, we have one from a similar time period, 1887, same composition, that white limestone, but it's quite easy to read because this one is in a desert where there's very limited rainfall, so there's also very limited chemical weathering. So this can really show you how climate is very important to our weathering processes, and then how soils can be formed. What we're seeing here, this is solid rock, right there. That's all solid granite. And then through chemical and mechanical weathering processes, we have all of this broken up material that has formed. And that looks like that. So a big solid piece of granite, like what you might have in your countertops, if it's exposed at Earth's surface to mechanical and chemical weathering, breaks down into stuff that looks like that. All right, soil formation. Soils form on stable surfaces. And what a stable surface means is we're not adding a whole lot of sediment, we're not depositing a lot of material, and similarly, we're not eroding a lot of material. So it's basically just sitting there. That's a stable surface. And these soils are going to form from the surface downwards. So as they get older and better developed, they actually get deeper and deeper into the ground. And this results in what we call horizons. And horizons are very distinct layers within the soil. And you can see these are many of the things that act on a soil that's being developed. And we get rain entering the ground, and you also get some organic material from any plants that are in the area. Worms churn around, and there's also like fungi and bacteria in there. You have the roots of the trees and other plants. Some of them will break minerals apart. Some of them will actually create acids and things. And this downward traveling water picks up some material and carries it deeper into the ground. So as all of these processes act, you start getting very distinctive layers developing in your soil. You get these distinctive horizons. And the way you study soils is you study a soil profile, which is looking at those distinctive layers. And so you need to see a cross-section, a side view of the soil. And how you do that is you dig a hole in the ground, and then you stand in the hole and you look at the soil layers. And how do I know this? Because I used to work in a soil lab, and I did a whole lot of digging holes in the middle of the desert to look at soils. And people wonder why I went back to school and worked on my PhD, because I didn't want to dig holes in the middle of the desert anymore. So anyway, see, you dig a hole, you stand in it, you look at the layers of this soil. Now, not all layers or not all soils will contain all the possible horizons. It really just depends on, the climate and the parent material and all that good stuff. But the layers you might see are shown here. And some soils will have all of these. The layer that's going to be at the surface is called the O horizon. O standing for organic material. And so this is going to be loose and partly decayed organic matter. Underneath the O horizon, we have the A horizon. And this is going to be some of that organic material that's partially decayed. We call that humus, not humus. And so we get some of that humus mixed with some mineral, some of the weathered rock. Underneath the, by the way, the O and the A horizon, that's where the majority of the nutrients are in the soil, and that is called the topsoil. Now underneath that topsoil, we get the E horizon. The E horizon is usually a pale colored, and this is where alluviation and leaching occur. Well, alluviation is the removal of small particles, and leaching is the removal of anything soluble, anything that can be dissolved. And the reason that happens, if we have enough water, meaning enough rain falling, it moves through the soil and it starts dissolving and picking up the smaller particles and carrying it farther downwards. Well, how far down does it carry it? Not that far down. Because once we get to the B horizon, this is also known as the zone of accumulation. And what's accumulating? All this stuff that's being removed from above. And so this is the accumulation of clay, iron, aluminum, and other materials from above. Below the B horizon, we get the C horizon. That's partially altered parent material. So now when we've reached the C horizon, we can finally see what kind of material did this soil develop on. Was it on sand? Was it on lava? Was it on limestone? We're going to start seeing little pieces of that parent material. And then underneath that, we will eventually reach the unweathered parent material. So in any case, that's the soil horizons you might see, not that you have to see them in every soil. Now, when we study soil and we're looking at those different horizons, we use various descriptions to distinguish between different types of soils. And one of the things we look at is color. And color is important in soils because that's related to the composition. And you can see I'm giving you some examples here where like a black or dark brown soil is organic rich, red and yellows indicate iron oxides, light gray or white means we don't have a lot of organic material, but often you'll have a lot of minerals like calcite in those white colored soils. We also, when describing soils, describe the texture of it. And in this case, texture refers to the size of the little fragments inside the soil. And they might be made from sand, which is 1/16 to 2 millimeters in diameter. There might be some silt, which is smaller than that, all the way down to 1/256 of a millimeter. Or you might have clay, which is the really, really tiny particles, really microscopic. And we care about the size of the soil fragments because this is important in agriculture. For instance, sandy soils don't hold a lot of water. The water drains away very quickly. Clay soils, clay tends to really clump together, and it can be difficult for, if you're trying to plant young plants with very thin roots, it can be difficult for them to take root. So often in agriculture, what you really like is loam. Loam is a soil that has kind of equal parts sand, silt, and clay. It has sort of enough silt and clay to hold water, but it also has enough sand that it makes it easier for plants to establish themselves. Now, when we describe soils, we also describe their structure. This is the tendency to form clumps. And in soils, we call these clumps of soils PEDs, P-E-D-S. And again, this is one of these things that's important in agriculture because depending how clumpy the soils are affects how plants will take root and also what the erosion potential for that soil might be. Now, I'm going to go through how in the United States we describe and subdivide soils, but I'm going to leave that for volume 2.